Are you picking up my voice? There it goes. Okay, good. Whew. I can see a little bar over here that tells me if it can hear my voice, and it does. So, okay, so we're going to talk about the trapezoidal rule. If we think back to the very first section in this chapter, we were looking at approximating area underneath curves by using rectangles. And if we instead go with some trapezoids, we get a little bit of a more accurate approximation of this stuff. So, give you an example here. Let's say we've got some curve, and we want to find its area from A to B. So starting here and ending there. And kind of like with the rectangles, we're going to break it up into these little subintervals, okay? And the more subintervals that we have, the more accurate it's going to be. But just to kind of keep it simple, I'm going to make these look kind of wide. Okay. Now before, like I said, we just chopped them off and made them rectangles. And we ran into a lot of overestimation and underestimation with that because the little corners of the rectangles would oftentimes be poking out of the area that we wanted or were caught underneath, and there'd be this large portion that didn't get counted that we wanted. So instead of making them come down and turn into rectangles, what if we just took each individual point on the graph where we have these subintervals created and just connect the dots? Okay, now take a look at the difference of the area that's actually underneath the curve and the area of all of those little pieces that I've just created by doing that. Do you see how the error in this situation is much less than doing it with the rectangles? It's a very, in general, minuscule difference in the approximate area versus the actual area that we have when we're doing it this way. And what type of geometric shapes have I made by connecting the dots? A whole bunch of trapezoids. Remember, the definition of a trapezoid is a quadrilateral, 4 sides, that has 2 sides, exactly one pair of sides, that are parallel. Okay? So like, I'm looking at, let's say, this guy here. There are your 2 little parallel sides, trapezoid. Okay? And if you remember from geometry, the area formula for a trapezoid is 1/2 height base 1 plus base 2. Okay? Well, let's take a look at this real quick. So the height now of each one of these trapezoids is actually going in this direction. Does that make sense? Because your 2 parallel sides, when you're talking about the area of a trapezoid, the 2 parallel sides are the bases. So it's like we've taken a trapezoid and turned it on its side, and we're doing it that way. So the height is actually going left and right. The bases are going up and down. So this would be like your base 1. This would be your base 2 kind of a thing. Okay? So if you know how wide they are, and all of the little bases of each of these as you go, then you can add up all these little trapezoids using that trapezoid formula and get it. Now there is a formula that kind of streamlines this process for you, kind of like we saw with doing the RRAM and the LRAM and all of that. So if we think of our bases as values rather than just bases, we're going to start to see there's going to be a little bit of overlap here. Okay? So do you guys see how base 1 is actually the value of the function at this spot? It's a y value, right? How far down did we go? Same thing here. How far down did we go? And then all of them, as we go across, these are all y values. of the function at different places. Okay, so think of it like this. This is A, then I'm going to make this x sub 1, x sub 2. This point will be x sub 3. This will be x sub 4, x sub 5, x sub 6, and then we finally get to B. Okay? So the area of, and A will make that x sub 0, and B will make that x sub 7, just so we can keep using the same kind of lingo here. So that's trapezoid right here then. Its area is going to be 1/2 the height times O plus x, f of that, right? So f of xo plus f of x sub 1. Okay? Then the next shaded in 1/2. Same height, right? Because we've split these all up so they're the same width. Of x1 plus f of x2 for that one. And then the third trapezoid, 1/2 of x2 plus f of x3. Okay, etc., etc. Okay, until we get to the last one. So, what patterns do you see in just this right here, in that big addition that we're making there with all of those little trapezoids? Trapezoid is going to have a 1/2 h in it, right? So that means I could out of the whole thing. So let's do that. So 1/2 h, that's going to leave me with f of x sub 0 plus f of x sub 1 plus f of x sub 1 plus f of x sub 2 plus f of x sub 2 plus f of x sub 3 plus etc. Okay, that definitely helps. Anything else we can do to make this a little more condensed? Do I see a pattern with the x's in there?
There's like 2x and 2
Mm-hmm. And that's going to continue until we get to the end. Okay, now think about this. Do you see how we have the first doesn't repeat, but the next one does, and the next one does, and the next one does? Take a look at the trapezoids up there. Do you see how every time there are two trapezoids that are next to each other that share an x value, that one gets repeated? As we keep going, what's the only other x that's not going to be repeated? X sub 7, the very last one, right? So if this pattern were to continue, we would have 2f of x sub 6, but only 1 x sub 7. So in general, anytime that you have a trapezoidal rule like this that you're going to be using, how to break up the intervals, the very first value, the a, the lower limit, and the very last x value, the b, the upper limit, are only going to be times 1, but all the ones in between are going to be times 2. Okay? And then it's just a matter of evaluating the function at all those different places in between and plugging them in. Okay? So, let's try this. Okay? So, I guess in general, usually denote this with a T, but this is kind of the general formula for that. And reminder that this would be like your A, and this would be like your B in that. Okay? But that's the idea. That's the pattern we're going to want to follow with this. Okay? So let's try it. All right, so let's do the trapezoidal rule. We're going to approximate the integral from 0 to 5 of x squared dx using trapezoids that have a height of 1/2. So let's put this thing together then. Okay? And we're not even going to draw a picture to do it. Let's just put stuff in the formula because we can do that. So it's going to be 1/2 h. Well, what's h? 1/2, right? So it's 1/2 times 1/2. And then we're going to start at 0. So it's going to be f of 0 plus 2 f of 0.5 plus 2 f of 1 plus 2 f of 1.5 plus 2 f of 2. You get the idea until we get to 2 f of 4.5 plus 2 f of 5. Okay, so that pattern just continues until we get to 5. Oh, it's not a 2. Sorry. Ooh, that's bad. Just f of 5. Not a 2 on the last one. Start evaluating x squared for these different values and just start plugging in there. So it's going to be 1/4 f of 0, 0. F of 1/2 would be 0.25. F of 1 would be 1. 1.5, that's probably like 2.25 or something, I think. Yeah. All right, so we're at 0.51, 1.5. So 2 would be a 4. 2.5 squared is 6.25. 3 would give you 9. 3.5, 12.25. 4 gets you 16. 4.5 gets you 20.25. And then f of 5 is 25. So it'd be like that all put together then. Okay? So, take out your calculator. Start multiplying and adding this all together. I'll do the same thing. Double check. We get the same answer. And then we're going to compare this answer to the actual value of that integral, because you guys can do that too. And we're going to see if we can figure out how much error we've produced doing it this way. So once you're done, you can check it out. That's what I got. You guys get the same thing? Those that are done? All right, that's good. Good calculator work, guys. If you are done, what I'd like you to do then is, because we are capable of doing this now, do that integral by hand. 0 to 5 of x squared using antiderivatives. Let's see what we get. Should be very similar, pretty close. The antiderivative of that is 1/3 x to the third, evaluated from 0 to 5. If you plug in a 5, you get 41.6, or about 41.7, I guess, if you round it up. Plug in a 0, you get 0, so it's 41.6 repeating. So, right? 41.875 versus approximately 7. We're not off by very much. So, we're going to do a little percent error. You guys that are in science classes do a lot of this, I imagine. Percent error. What do we remember? What's the first step in the process? We've got to figure out what? Exactly. How off are we? Before we convert it into a percent, we just need to figure out, like, physically how much off is it. So we would do 41.875 minus 41.6 bar. And then that's absolute value because we want that difference to be positive, right? In this case, it comes out positive, but always is absolute value of whatever you get there. And then it's that difference. What do we do with that then? Divided by what? The number that we're supposed to have, which is what? Which one is the one we're supposed to have? 6. Yeah. Okay. 6. Okay. So it's like, what was it? Measured minus expected over expected, or something like that. Forget how they say that. Okay, to that effect. And if you need to round off a little bit, okay, fine, that's all right, because 6 bar you're not going to get exactly necessarily. So the difference here, though, 41. I'll do 41.667 just to keep the same number of decimal points there. 0.08. So we have a difference of 0.208 out of a total of an expected value of 41.6. So that divided by 41.667 again will go. So I'm getting 0.00499. Now what is that as a percent? It's approximately 0.5%. Not too shabby. We're only off by 0.5% of what we wanted. Okay, so now that you guys can do integrals, they're going to have you doing a bit of this work as well. Okay, calculating what is that percent error once you go through and use one of these processes to get an answer. Okay, so way, in addition to the trapezoidal rule. We'll come back and practice this a little bit more later, but I wanted to get this other one out there too. This other way of doing things is called Simpson's rule, not related to the cartoon on Fox, but some guy named Simpson that came up with it. So, in fact, you have a little thing in your textbook that's a mathematician that came up with it named Simpson. I will leave that to you to read if you would like. But here's the gist of what Simpson's rule does. Simpson's rule takes some sort of curve, and again it has some sort of consistent interval that's created. Okay, so the height of those. On top of one, rather than making a straight line from one point to the next, what Simpson's rule does is it makes a little parabola piece on top of each one. Those are each little parabola pieces that kind of way around. And because the parabola can be curved, it can more closely represent what you have. Okay? So if you were actually trying to area underneath Simpson's rule would be perfect. The percent error would be 0. But if you were doing something like a cosine wave, or maybe like a natural log, or a cubic function, or something like that, that's not exactly in a parabola shape, but it is curved, it'll get really, really close. The percent error on these guys is super duper tiny. Okay? Now, the Trapezoidal rule, I went through and derived kind of why the formula is what it is. Simpson's rules is a bit more complicated that way. And I don't want to spend a lot of time doing that. But in the book, they kind of through a bit of an explanation of that and an exploration. If you want to check it out, you're welcome to, but I'm guessing you guys aren't. So we can start using it, though, okay? So rule, we did T. Simpson's rule is denoted with an S. So his rule looks like this. It's 1/3 H. And then you got f of x sub 0. And then in Simpson's rule, it has a pattern where it starts 4 times f of x sub 1 plus 2 f of x sub 2. And then it kind of continues to go back and forth, 4, 2, 4, 2, 4, 2, 4, 2. Until you end up at a 4 again. So I'm going to say f of x sub, that's an n minus 1 if you can't see that. And then the final one is just f of x sub n. So the issue you're probably going to have with this one is being able to play the coefficient game correctly. It goes 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, as long as you need, and then it stops 4, 2, 4, 1. You're done, depending on how many intervals you have. Okay. Now, because of the fact you need to end up at a 4, some of you guys might be thinking, well, what if my number of intervals is such that I'm going through this pattern of 4, 2, 4, 2, 4, 2, and I end up at a 2, and then my next, or my next, what the heck? I need to stop the last one. So the number of sub-intervals that you have to be even. If it's odd, it doesn't work. Then you get trapped at the end and you can't finish the pattern. So you have an even number of subintervals to get this thing to work for you. So now usually you guys aren't going to have to really worry about this because I'm going to set up the problem for you. I'll say use Simpson's rule and use 8 subintervals or something like that. So I'm going to make sure that you have an even number of subintervals so then you can go ahead and do this. Okay? It's not going to be very often that you're going to have to determine how many subintervals you want to then go and put it together. I'm going to kind of set up those parameters for you. So let's use Simpson's rule to approximate the integral from 0 to 8 of f of x dx if f of x equals, what could we do for this one? Let's go to the 4th. And we're going to use n equals 8. So n, you're going to see, that refers to the number of subintervals. So we got 8 subintervals. So if we're doing an integral from 0 to 8, and there are 8 subintervals, what's the height of each interval? 1. Okay, so we're going to use an h of 1. Okay, so I'm going to have 1/3 times 1, and then 0 plus 4, 1, plus 2, f of 2, plus 4, f of 3, plus 2, f of 4, plus 4, f of 5, plus 2, f of 6. See how my pattern's going to work out nice for me now? 4, f of 7, plus f of 8. Okay, so I like that. Now, like I said before, just like with the trapezoidal rule, I got to figure out what all of this f of 0 through f of 8 actually is. Plug those numbers in and see what we got. So I'm going to freeze it right now. Do that. You guys go ahead and do that too. Let's see if we end up with the same thing once we're done. And then we'll do some percent error calculation again and see where we're at. This is going to be huge. Now, obviously, for questions like this on your tests and stuff, um, is use calculators to do it. Okay. Now you can always do the integral on your calculator as well. It's always going to be a little bit of error from one to the other, that sort of thing. So you're still going to need to know how to do this process. On your test, multiple choice, I will probably put it on the non-calculator part and hand you a little like scientific calculator to do it. So you can still type in all the numbers and not have to try and do that in your head. So in any event, I could have gotten something on the order of about 33,000 for this one. You get the same as me there. 32,773 and a third. So if you didn't, here are my numbers. I don't know if you guys wrote all yours down too, but you can check that out and see if you got something different. Maybe look and see what I was multiplying and adding there. See if that matches what you had. But I'm pretty sure I typed it in right here. Should have been about 32,000 there. Yeah. Now again, if we do the actual integral of this, which we can do now, we can check out that answer and see how it came. What's our percent error this time? So the antiderivative of this should just be x to the fifth, right? Because you'd bring down the 5 and it would be 5x to the fourth. So from 0 to 8, 8 to the fifth minus 0 to the fifth should be what we've got here then. I've got 32,768. Pretty darn close when you consider the fact that our first 3 digits are all accurate. So, knowing that, and again, I'll freeze it and do the same thing, but go ahead and run a percent error on this one. Let's see how close we got. So is Simpson's rule pretty accurate? Yeah. I got about a 100% when I did mine. Let's see if we got the same thing here. 0.0163%. Okay. So, yeah, that's, well, between 1 and 2 100ths of a percent, which is pretty darn close. We had a difference of 5 when we're talking about numbers that are like 32,000. It's really, really close. So, now for this particular integral, if you're trying to figure out the value of an integral that's of 5x to the fourth, this one we can do by hand. So in practice, would Simpson's rule be something you would need to do for this particular integral? No, because we got a perfectly good method that we know gets it exact, doing it this way. But what if I were to give you some integral that you have no clue about? You have no idea how to do the integral yet, because there are lots of them out there that it's going to be a while before we can do it. So then, at that stage, if you need a number to work with, but you have an integral that you can't do and get an exact answer for, Simpson's rule, or maybe even the trapezoidal rule, would not be a bad way to go to help you get through some of those problems and get an answer, and so you can use that to move on and do whatever else you need to do with it. That's why these two things exist. So you can do stuff like that, okay? So think guys one more to do. I'm going to make it not so many intervals so you can do it quickly, but I'm going to give you an integral to do both the trapezoidal and Simpson's rule 2, and then compare the percent error of each one and see what you got. Okay? And, let's get going on your homework and such. So we're going to use the trapezoidal and Simpson's rules using n equals 4 to approximate the integral from 0 to 4 of the natural log of x dx. All right, and then I will give you the exact value of this, and I'd like you to use that to calculate your percent error for each. Oops, you can't go from 0 to 4. 0 is undefined. 1 to 5. That will work a little bit better. As soon as you start playing numbers, it's going to be a problem. Take this out to 5 decimal places for you. So when you're done with all your calculating with each of these, do the same thing. Round it off to 5 at the end, and then compare it to that, which is the actual area underneath.